Hello everybody, thank you for watching. This is our 9.9 video on the ideal gas law. In this video, you'll explain the behavior of an ideal gas in terms of pressure, volume, temperature, and the number of particles. Let's first talk about what is the ideal gas law. Pressure, volume, and temperature, and the amount of an ideal gas are related by one equation. There are multiple scientists that contributed into this entire gas law formula, and some of those scientists were Robert Boyle, Charles, and also Gay-Lussac. What is the ideal gas law? The ideal gas law has a specific formula. The formula for the ideal gas law is PV equals nRT. Our P stands for pressure, our V is for volume, N is the number of moles, R stands for our gas constant, and T stands for temperature. When we take a look at our gas constant is a constant number that you're going to be able to use. The gas constant R equals 0.08206 atm liter divided by mole degrees Kelvin. Whenever you're using the ideal gas law, you always need to pay attention to our units. Because our gas law has these units in it, our pressure always has to be calculated in atm in order to use this formula. Our volume always has to be in liters. Our number of moles are always going to be obviously in moles, and our temperature always has to be in degrees Kelvin. Because if you take a look at the units for the gas constant, it's atm liter divided by mole Kelvin. In order to use the gas constant, each of these other variables have to be in the proper units. If you don't remember how to change temperature to Kelvin, don't forget that you just have to add 273 to our degrees Celsius. Let's take a look at some example problems. So we know the formula is PV equals nRT. If I have 4 moles of a gas and the pressure is at 5.67 kilopascals and our volume is 12 liters, what is its temperature? The first thing I want to do is just make sure I have proper units. Our pressure has to be in atm, so I need to convert this to atm. Our volume is in liters, which is good. We have moles. We can use our gas constant, and we want to calculate our temperature in Kelvin. So when I set up the problem, I'm going to see that I'm going to have these as our variables. Lastly, doing a little bit of algebra, we're just solving for our temperature. So we're going to multiply and then divide to set temperature by itself. I'm going to get an answer of 2.05 Kelvin. Let's take a look at another problem. If I have 21 moles of a gas held at a pressure of 28 atm and a temperature of 20 degrees Celsius, what is the volume of the gas? We do have our pressure in atm, which is good. We're trying to figure out what our volume is. That's going to equal the number of moles. We can add in our gas constant and change our temperature to degrees Kelvin. When you do the math, you're going to see we're going to get a volume of 18.03 liters. Let's look at a third example. What I want you to do is please pause the video and then come back to see if you get these answers correct. In this problem, it's giving you liters, it's giving you PSI, which you need to change to atm, it's giving you 10 grams of XeF4, which you need to use molar mass to convert it into moles. We have the gas constant and we're calculating for our temperature. When we're doing this, we can see that we have this really huge number as our temperature. So hopefully you got this answer correct. If you wanted to change this answer to degrees Celsius, all you would need to do is minus 273. Lastly, try this problem. This is our ideal gas problem and it is a big problem, so please pause the video and figure out. A deep underground cavern has 2.24 times 10 to the 6 liters of methane gas and has a pressure of 1500 kilopascals and a temperature of 42 degrees Celsius. So we want to figure out how many pounds of methane does the cavern contain. Don't forget our conversion, 1 pound equals 454 grams. Hopefully when you calculated and did a whole bunch of conversions, you can see that the number of pounds we're going to get is 4.5 times 10 to the 7 pounds of methane. And that concludes our video for today. Thank you for watching.